I will derive the zeroth order, first order, and the second order chemical kinetics. First, we'll look at the zeroth order reaction. It's zeroth order. The reaction rate R is equal to reaction rate constant K. R does not depend on the concentration of any reactant. How is that possible? We can just use this example. The electrolysis of water. Because this water on the left-hand side of the equation is a pure liquid. Its concentration never changes. It's roughly 55.5 mole per liter. Therefore, the reaction rate never changes. It's a constant here. And how do we derive this equation? First, we need to know that if we have a reaction of zeroth order, and R equals K, again this is zeroth order, so I can also say it's K times A to the power of 0. And this is the reaction rate. How do we define the reaction rate? It's simply how fast the product is produced, or how fast the reactant is consumed. And it's really easy to solve this differential equation. So what we will do is I will erase this A to the power of 0. This is simply 1. And I will use K equals negative dA over T to solve this equation. So we go from here. dA equals negative K dt. And now we can integrate both sides from time 0 to just any arbitrary time t. So from time 0 to a arbitrary time t. Again, from time 0 to time t. However, to be more rigorous, we need to change this dummy variable t to t prime, because we used t as the upper limit of the integral. And then we simply integrate both sides. This one is simply just a. We go from 0 to t equals negative k t prime, and t prime is from 0 to t. Alright, then I'm going to erase this part so that we can go up here. It's going to be the concentration of A at time t minus the concentration of A at time 0. This is the initial concentration of A. And then we plug in this t to t prime and 0 to t prime. And then we slightly simplify the equation. Now we know how the concentration of A changes with time. And then we will derive the half-life for this A, the zeroth order reaction. So what does this mean, half-life? It simply means this guy is equal to half of the initial concentration of A. Therefore, again, this guy is half-life. And we solved this simple equation. We learned this half-life of the zeroth order reaction is simply A naught over 2K. We're done with the zeroth order reaction now. Okay, first order reaction. First order reaction, again, I'm going to give you an example here from A to P, but this time the reaction rate is proportional to the concentration rate. So again, we know the reaction rate is how fast the product is formed, and it is also how fast the reactant is consumed. So we have this equation, we also have that equation, and we are looking at another differential equation here. We will separate the two variables, A and T. Okay? And then we will integrate both sides from time 0 to time t. And again, this t is a dummy variable. It doesn't matter if you use t or t prime or alpha or beta. So we're going to just do this. This integral is the natural logarithm of a. From time 0 to time t is equal to negative k. Again, you just plug in t prime equals t prime equals 0. And again, I will erase this part. And then we're going to plug in the concentration of A at time t and the concentration of A at time 0. Is equal to negative kt. All right. The concentration of A at time t is simply then A naught, the initial concentration, times this exponential function. Now we're going to work on the half-life. This is when this concentration of A, which is 1/2 of the initial concentration, is equal to A naught. I'm going to plug in this half-life here. Again, this guy is my half-life. For the first order reaction, you can see this to cancel. This part is 1/2. Therefore, kt 1/2 equals ln2. And the half-life is ln2. Done. I will erase this part to do the second order equation. So this is a second order equation. In another video, I showed how to derive the second order rate laws and half-life for a reaction that involves two different chemicals, A plus B, to produce P. So, but now I'm going to just show you how to do 2A producing P. It's going to be a little bit different. Again, we're going to look at the reaction rate. Reaction rate is this, how fast the product is formed, and then we're going to do this. And we'll have to stop here and think. To produce 1P, we have to consume 2 A's. So the consumption rate of A is twice the production rate of P. Therefore, we have to include this half here. And again, we're going to use this equation. And then we separate the two variables. And then we integrate both sides from time 0 to time t. Again, this t is a dummy variable. So this time I'm going to use a Greek letter. I'm going to use beta here. It does not make any difference because, again, if you integrate this, it's 2k beta. And you have to plug in beta equals t. And beta equals 0. So the result is 2kt. Now over here, the integral of this is just 1 over a from time 0 to time t. And then basically it's the reciprocal of the concentration of A at time t minus initial concentration of A. Look at this part, look at this part, and we're going to say, well, the reciprocal of the concentration of A at any given time t is the reciprocal of the initial concentration of A plus 2 kT. That's the rate law of the second order chemical kinetics if we have 2A as the reactants. Now we're going to do the half-life. This time I'm going to just transform this equation. I'm going to plug in the half-life concentration of A here, which is simply just half of the initial concentration. I'm going to replace this T with half-life, and then we can easily see the half-life is 2K A naught. Done.